Hello, welcome to Networking Field Day 14. You are about to watch a presentation from Kentik that includes a group of invited social media influencer delegates who are here to ask questions, make comments, and offer their opinions about the technology of Kentik. If you'd like to learn more about this and other videos in the series, please go to our website at techfieldday.com or check out our YouTube channel at youtube.com/techfieldday.
Good morning.
Morning.
Sounds like, you need to go.
My name's Dan. Hi, Avi. Welcome to Network Field Day. I am responsible for the engineering group at Kentik and product development. And today we're going to talk a little bit about the engine that actually runs behind the scenes, that does the things that Avi talked about and what he showed in the user interface. So a little bit of stats about the engine behind the scenes. We process, and Avi needs to update his slide, we process about 125 billion flows per day at this point. We're doing over 1 million flows per second at peak. We run about, on a continuous basis, over 50 what you would think of as SQL queries per second, which actually turns into thousands of subqueries per second continuously. We're storing about 75, or we're technically storing about 75 terabytes of flow per day, but we compress that to about 25. And we're taking SNMP, BGP, network performance, and NetFlow to make this happen. I was afraid a Bluetooth clicker was going to be too advanced. Okay. So if you think about it from a high level, we had to build a very large distributed system to make this work. And the first step in processing NetFlow is you have to take a whole bunch of data sources. Well, let me back up. The first step in making a usable product for network people is you need to process a whole bunch of data sources, as Avi mentioned. So we call the ingest layer the fusing layer, and we're going to talk a little bit about exactly how that works at scale. We then take the output of that, which essentially is one, you can think about it in a traditional database as one row of data. We store it into a database. And then at the same time, we have to have a stream-based processing system for anomaly detection. And we'll go into all three of these. So before we started building our own, we evaluated, as Avi mentioned, a handful of different databases. And none of them could handle the multi-tenancy, the fairness, and the scale that we needed specifically for network operators. We had a bunch of databases that could definitely store the data, but nothing that could give the results back in 2 seconds, which is what we needed to do to be able to actually splunk into the data in the way network people want to.
So just a quick question when you hit on the multi-tenancy. So if you're an upstream provider, let's say you're a data center ISP and you've got tenants, you can then offer that as a multi-tenant solution?
So from our perspective, multi-tenancy today is allowing us to have one SaaS platform with all the customers on it.
Okay.
Right? Tomorrow, which would probably be, let's say late 2017, we will actually provide sub-multi-tenancy as we will define it.
Gotcha.
Right?
Yeah, that makes sense.
The challenge we're having there is, we're working through the steps of it from a data security and protection perspective. The challenge is actually building a UI. Every single person that wants to present something to users has a whole different description of what they want to present and how detailed or how not detailed they want to go. So that's really going to be the challenge. So the architecture of the system is we've got data sources on the left, which is the SNMP, the BGP, the host data, the performance data. We bring it into a fusion layer, which we're going to talk about. We store it, and then we've got a query layer that can query that storage. And then on the right-hand side, we have users, which could be SQL, could be REST, that could be the UI that Avi showed. So the ingest layer, we're going to go through each of these kind of phases of the ingest layer. But again, on the left-hand side is where you're seeing the data actually initiate. And the first step from a distributed system is you need to figure out a way to make any one server not a single point of failure. And you need to be able to scale this thing infinitely wide. So whether we started with 100 or 10,000 flows per second and now we've scaled it to 5 million flows per second, in the perfect world, you just add more servers and make it wider. So at the very basic first step, we bring this into an Anycast BGP VIP, right, which is doing the handling of getting this across a handful of what are called load balancers, right? The next piece would be, we call them relays, but they're actually equivalent of something like HA proxy or Nginx, but you think about it for NetFlow and for SNMP and for BGP. All right, so we bought application-specific load balancers, essentially, and we have a handful of those taking the data in from the BGP. Any number of those could fail, and the system would continue the process. And this is a different proxy than what Avi mentioned. Avi talked about a proxy people could run on site to encrypt the data. This is a proxy inside our infrastructure. And what this is actually doing now is taking the output of the load balancers and actually beginning to do intelligent things with the data. And you can think about it, since this is behind the load balancer, we can run these, we could run hundreds of these things wide from a distributed perspective. And these are starting to actually begin to do some processing. They require a reasonable amount of CPU. And these are doing things like, what kind of the data is the customer sending me? Is it a BGP connection? Is it SNMP? Is it NetFlow? What flavor of NetFlow is it, right? What's the sample rate the user is sending us? Maybe the user's contracted for only so many flows per second according to their business case, but they're sending us 10 times that because they're being attacked right now. What do we do with that data, right? We need to throw it away potentially, but at the same time we need to resample it, because if you throw it away and now someone's looking at a graph, they could actually see a dip where it's actually an attack. So this is the actual layer that's saying you're limited to 10,000 flows per second. You're sending me 100,000. I'm going to throw away 90,000 of them, but the 10,000 I have left, I'm going to change it to say that I've sampled 10 times higher. So the representative graph looks the same, right? And then the most important part of the proxy is, this is the guy that actually says, from a distributed systems perspective, I'm going to launch a child process that's actually going to now be responsible for taking all of these disparate data sources for this individual device, merging them together, and monitoring the health of that child, right? And we call that child the client. And this is actually where the magic occurs on the fusing of all the data. And this is kind of one of the most key pieces to the back end. Now you can see the client is taking NetFlow, and it's taking BGP, and it's taking, let me see if I have that on the next slide for a second here. Yes, we'll move into that. Okay, the client's taking your data sources in, and it is essentially outputting something that's going to go into a database, right? Syncing all of this data together, and we'll talk briefly here on how that actually works. The first step is the client has to convert the data to some sort of normalized data source. So you're taking IPFix in, or if you're taking SFlow in, or you might even be taking KFlow in from a host agent. It should turn that all into one common output, which it does. It turns it into KFlow, right? So KFlow is this, Avi's talked about this before, it's this expandable structure that is extremely lightweight, that we can put all the NetFlow data in, plus put the SNMP data in for that particular NetFlow record, plus eventually we can put maybe DNS information in there. We have the host data for performance that goes in there. Right, and it does this very, very quick and lightweight. And we're actually using Captain Proto, which is a variant or a newer version you can think of protobufs. So now that we have the input data normalized in some structure, now we need to begin to take all the other pieces and merge them in. So we've got a little bit of buffering we have to do here to take multiple data sources in. We've got some, a huge n by n issue here. You're taking in a large number of flows, and you've got a gigantic BGP table and a gigantic list of tags. So you've got to find very efficient data structures to merge these multiple pieces of data together. You have app-specific data, which you may have a DNS feed coming in that could actually be delayed by a few seconds. And now you've got to wait for that and merge that data in, right? Threat feeds is something that's coming, and somebody here, we were talking about Splunk and logs. We're actually working on the ability to actually have logs, like somebody did a router reboot at this particular time, and I want some indicator to be put in the flow as well with that. That's a coming soon feature. Then you put it all together, you have the client, which is in the flux capacitor there in the middle. It's taking all the data in from the left and from the right, merging it together into one row that we're going to put into, let's call it a network-specific database. And this is one of those examples where people say, well, why didn't you just use Hadoop, or why didn't you just use Elasticsearch? And no matter what, you need to do this, whatever system you're going to use, right? So this was one of you begin to break down the pieces if you're going to use a third-party database, and you begin to realize that even if you had a database that did everything you wanted it to, a significant amount of your effort is still on the edges of, you need to do it anyway. So that begins to make you wonder whether you should use a generic database or build your own, if there's big advantages to building your own. And I mentioned before, the last step that this client does is this resampling, where it's got a hint from the proxy saying they're sending me too much data, and now the client is the one that actually group the data together, throw away the data, and resample as necessary in this situation where you're over a contracted amount from the customer. So the next layer is the storage layer. How do we take this? We started with 1 million flows per second. We merged all this data, and we still have 1 million flows per second coming out, assuming that we don't have to resample anything. And that's a lot of data to store. So we needed to build a distributed database that was very specific to network operators. So it's taking the input as Kflow, and it's the same idea. It's going to break this Kflow data into small chunks, and it's going to shard it as wide as it needs to go in order for us to have reasonable performance. So we have found, for example, that a particular server with the SSDs and with 48 cores can do, I'm just going to make a number, can do 100,000 flows per second. And we just continue to add them wide as needed for performance. The problem with sharding is somewhere there needs to be the master metadata, which says this particular device has this particular shard on it. Right? You could try to do that in a deterministic hashing method, but the problem is then if a server gets hot and you want to move something around, you lose that ability to go back in time and say, well, last week it was on this server, but now the new data is on this other server. Your whole hash ring changes. So you actually do need this parent database that we have, which kind of says for this time, for this device, for this piece of data, it sits on this server. Right? But it's a very, very small amount of data compared to the amount of flow you're receiving. Less than a hundredth or a thousandth of the percent. Finally, we take this data and we actually put it into a column store database, right? And then the last thing we do is we compress it using ZFS. So now we actually have the data on disk. And now we need to do the other side, where let people actually query the data. But the query side is where we begin to now have challenges where we need to make sure that we're fair. We can't let one person run a query and monopolize the entire system. But at the same time, we don't want to say each user only gets 1/10 of the system. We want to say if the system isn't under any load, then you get 100%. And as soon as the second guy begins to hit it at a query, then you get 50%. And we've managed to engineer that. And that was quite a challenge, actually, because you end up with a queue of things to do. And if somebody happens to be asking the system for a very big query, and then a second guy comes, you have to immediately slow down the amount that first query is doing and let the second guy have some resources. You can't wait till the first query ends and then begin the time slice. Security has been a huge issue. Fundamentally, down to the lowest levels of the database, we've had to make sure that one customer can't see another customer's data. Right? We have to make sure that if there's a SQL injection or anything happens from the UI level, that the actual database engine itself is prohibiting that. And we've done that by passing down user information all the way down to the lowest level in the database. And then something people forget about is caching. So we have a caching layer, and we got burned a couple times because we built all this fairness in and we built the security in and we didn't think about it on the caching layer. So you need to make sure that even at the lowest level, even at the caching level, you're doing fairness as well. If somebody's asking for a gigantic query and it's all in cache, to make sure that that one person can't monopolize the cache engine. Right? So we've managed to succeed that as well by, again, it's the same idea of looking at how many jobs you have outstanding, leaving some headroom, and then doing fairness based on each company that's running a query, not even each user. The companies have fairness. And then the question is, how do you begin to query this data? So we've built this underlying multi-tenancy sharded database, and we actually use Postgres as an interface. And we use something called foreign data wrappers. So when you ask Postgres to query, Postgres doesn't look on disk. Postgres doesn't attempt to process it. It does all the syntax processing for you, and it hands you the query in a structure. And then we take that query in the structure and we break it into our thousands or millions of shards. And we actually return these shards individually back to Postgres. And it actually just thinks it asks the disk for it. And it puts all the pieces back together and hands it back to the user. So it's kind of like Postgres is aggregating our sharded database for us, but it lets us use a common language. And it's worked out extremely well. And Postgres does support multi-user and does a very good job of the multi-tenancy for us as well from a high level. And early on, I think the original intent was all we have to do is give people a SQL interface and we're done. And maybe a very basic UI. Who wants to use a user interface? People will type SQL statements. And it's not quite the case. So now we had to spend an enormous, I'd say half of the development effort is building a user interface that's network and traffic specific. You can't just hook Tableau up and expect it to know what a CIDR is, right? Or know how to expand a BGP path. So enormous amount of effort in building a UI that then behind the scenes makes RESTful calls to a middle layer. And that middle layer is actually making SQL calls. So our entire UI is driven around SQL statements. And then finally, we had to have a REST-based API. Because again, we found that network operators don't want to write SQL statements. If they're going to build their own portal, they want to make a REST call. Right. So they're kind of our 3 ways to actually get access to the data.
Just curious, just a quick question. So, you guys have invested a lot of time in BGP because it's part of your use case. Hey, have you ever looked into any other routing protocols? Or is there value in getting into any other routing protocols for what you guys do?
We have looked at them, and the answer is yes, we will eventually have to get into them as we move more into the enterprise case. But it's not something that, it is something we will go to. It's not something we're doing today.
Gotcha.
Right.
A lot of service providers use IBGP as an IGP
Sure.
Substantially, but we've also seen, I don't know how many people use packet design, but we've seen a lot, you can get really stuck in the depths of every IGP and need to preserve our bandwidth. But
Sure.
yeah, it's a not yet for us.
Yeah, I just didn't know if there was any value in having those metrics with the way you're dealing with the BGP routing data in the big picture.
Yeah, there can be definitely for the inside of the network, which is definitely we've not written off. We have people doing it. We just aren't doing that yet.
Yeah, it's a hard problem to solve.
Yeah.
No doubt.
Yeah.
One of the big challenges that service providers are up against, we'll start with the service provider world, is NetFlow and most of the analytics platforms do a great job of showing you where the traffic entered your network. And if you know specifically what you're looking for, you can tell where it exited the network. But what they don't do a good job for is saying, for this piece of data I'm looking that entered the network, I want you to tell me where it left it 10 hops away, right? So using BGP, we're beginning to be able to do that, and then you can put costs to the network and things like that. As we move into the data center, we're going to have those same challenges with IGP, and that's where we're going to need to begin to look at consuming IGP data.
Sure.
Right. Avi, I don't need to move through the UI, but this was just showing the fact that we have UI as one of the methods. We have SQL as a method. And the interesting thing about SQL is we fully expose and document in knowledge bases and via the actual Postgres what the entire table schema is. So you can go in and say, these are the 50 columns you can actually query, right? And it's as simple as, is it packets you want to look at, or is it country, or is it geo, or is it site? Whatever you want to, you can write a very simple SQL statement. And here I just wrote one in a few seconds. It says, show me the top 5 protocols, how many bytes they're doing, or megabytes per second they're doing for every device in network that's doing about 100 gigabits per second, right? I was going to show you the analyze up here. That query took, without it being cached, took about 100 milliseconds to run, which, again, our goal was to have a UI that was 2 or 3 seconds fast. So your queries have to be less than a second by the time you bubble it up. And then finally, there's JSON, again, fully documented. If you wanted to call the system and give it a JSON request, you can, and we'll actually build that JSON request for you. You can go into the UI and build this beautiful query using the GUI and then say, tell me what the JSON is. It makes it very easy for people to integrate with the platform. So we built this great database, and let me see if I have a slide here. One of the biggest things that has always been a challenge for me running networks is you run into a network operations center, and this is a great example. There's 30 people sitting here watching 200 monitors, and they're looking for bumps on the graph, right? And it makes you wonder why in 2016 we're still staring at graphs looking for bumps. Shouldn't the system be telling us that, hey, there's something out of line here, begin to go investigate it? So we wanted to build an anomaly detection system that would be both network and NPM specific, right? So tell me if for some reason I'm usually doing 100 packets per second or 10,000 packets per second to this particular network, and right now I'm doing 1 million packets per second to it, or I'm doing 2 packets per second. But it also should be NPM specific. Look at all my AS paths and tell me if retransmits on any one AS path suddenly went up, or application latency went up, right? It needs to be completely customizable. If I ask anyone in the room here what you want to monitor in your network and what's important to you, every single one of you is going to have a different answer. Right? A DNS provider wants to know if traffic to an individual country changed. ISP wants to know if traffic to a CMTS or a head-end changed. Completely different set of requirements. So we can't just provide people 10 anomaly detection rules. They have to be able to build them from scratch, which is a double-edged sword because it's complex, but it's also extremely versatile. And we can't just look at top-level things. You can't just say traffic per interface or traffic per device. We need to actually get very granular and say, I want to look at all the traffic to the top 1,000 IP addresses in my network. And if any of those change, I want to know about it. right? Or I want to look at all the autonomous systems I send traffic or receive it from. And you'd be able to do over and under. And baselining is critical. Right? Sometimes I want to use a static value. If it's over 10 gigs, it should never happen. Or sometimes I want to say if it's over 2 gigs and 200% of what it normally is for this time of the day. Right? So when you begin to put this all together, you think, how do you do this? And then obviously you want actions. Right? There should be a nice UI that gives you nice dashboards, but then it should be able to email or Slack or JSON or PagerDuty. And finally, you need to integrate with mitigation companies, because the biggest use case for anomaly detection is DDoS. Right? So what do you do when you detect it? Notifying somebody that can go write an ACL, that's great, but it's even better if it can just integrate with two-way communication to a mitigation platform like your Radware or A10. And just tell that system to go deal with it. So how do we do this? So V1, we said, hey, this is easy. We keep so many minutes in RAM for our KDE for the engine. We'll just run queries every 30 seconds, ask it for something, and we'll look at that data and see if it's good or bad. And that was great for the first 6 months until we realized that we have hundreds of users running tens of queries, and this is turning into thousands of queries per second, and that's becoming a little bit abusive. And besides that, if I want to go back and compare it to the last 4 weeks, trying to run a query every 30 seconds for what the last 4 weeks' data is definitely not something. It's fine from a UI perspective. It's fine to do a few times a second. It's not fine to do tens or hundreds of times per second for the anomaly detection system. So what we needed to do, we needed some sort of stream-based processing system, right? Let the data come in, and while the data is actually flowing in, we want to actually process it in real time, right? Throw it away after we process it, but before we throw it away, take what's important and begin to build baseline information, right? Now we're just storing aggregates about what that user actually wants to look for. We're throwing everything else away after we process it. But our mindset was kind of trying to always avoid streaming databases or aggregation databases because it lost resolution. So there was kind of this initially there was this fundamental kickback where we don't want to use a streaming or aggregation database because that's going to make us be like a lot of our competitors that you're only storing aggregated data. But then we realized that if you do both, use a streaming database to detect bad things, and then circle back and reference your full granularity database when people actually want to drill into it, it comes out to be an excellent combination and kind of marry the two together, right? And we had evaluated for the streaming all sorts of existing platforms, right? Spark, Storm, SAM's pipeline database. None of them would do the scale or the capabilities that we needed. Because remember, we're network specific again. We want to do these weird things like look at CIDRs or look at AS path or look at one piece of the AS path, right? So we wrote our own. So if you looked at the original picture, it's kind of grayed out here. This was the whole flow of the system, but you've got the streaming layer. After the data comes out of the client, it's all fused together. We send one copy of it to the back end to store it, and we tee it off, and we send another copy of it to the streaming engine, right? So how do you build a streaming engine that can do 1 million widgets or 2 million or 10 million widgets per second and keep historical information, and every one of your customers might have 200 or 300 policies that they want to look at? And how do you do this and scale it and be cost effective?
You take twice as long as the CTO tells the CEO it's going to take to implement. That's how.
Isn't that anything in networking?
Scotty's rule of engineering.
Yes.
Yeah. Multiply your repair estimates by a factor of 4.
So if you think about this graph is working top down, what we're doing is we're taking these hundreds or millions of flows per second, and the first step we do is a user says, I want to look at traffic going to Comcast, and I want to detect if it's over 200% of what it normally was. Well, that tells you at the first layer you have a policy that says I only want to look at traffic at Comcast. You can throw everything else away, right? So you think about we take this data in for a particular company, and we kind of duplicate it across all the policies, and each policy is now only looking at the data that particular policy needs to look at. And then we begin to aggregate it, right? They only care about traffic to Comcast. That means we don't really need to know IP addresses anymore. We don't need to know ports. We don't need to know anything. This particular policy isn't looking at that. So now you're taking these tens of thousands of flows into that policy, and you're aggregating it down to 1 second buckets of just traffic. Here's how many megs I'm doing to Comcast. Or maybe they want to say megs to Comcast by protocol. So now you're just having 5 or 6 outputs from this. You started with tens of thousands of rows. You've got essentially 5 rows on your output, and you're doing this every second, right? And now the user says, I want to look at this every minute. I want you to say over a 1 minute period if something exceeds something, right? So now you know you've got 1 minute buckets. So remember each layer here, you can think of a whole separate set of servers in the infrastructure if you need it to go that way. You can co-locate this stuff, but then as you scale, you can break it apart. right? So you could have done the first and second layer clearly together, but now you begin to have a challenge when you scale. You can't break those two pieces together and make the system wider. So the second layer now takes this, what is now fairly low resolution compared to the input, and puts it in 1-minute buckets, because that's what the user is interested in looking at. Right? So now you're essentially outputting protocol to Comcast every minute, right? Instead of you starting with tens of thousands of flows per second. And you're going to take the second layer, and now it goes into the third layer. We're actually going to do the comparison. So they wanted to know if the traffic to Comcast was over 10 gigs, I want to be alerted. So that's easy. It's just going to do a static comparison, and then it's going to perform an action. Or they want to know if it's over 2 gigs and more than 200% of normal. Well, now this becomes challenging. Now what you have to do is begin to take this data and think about building a histogram every hour, and taking that histogram and storing that for the last 20-some days or 30 days or whatever the heck the user defined that they want to use for the baseline, right? But again, you've started with hundreds of or tens of thousands of flows per second, and now you're just storing a histogram of a few data points for each protocol for each hour for 21 days. It's a small amount of data, and you put this in RAM. You can actually store all the customers for these baselines, even tens of thousands or hundreds of thousands of these things in RAM. You persist them to disk for when you do restarts and code upgrades, but essentially what you're comparing every minute is in RAM now. Right? Now you can do all sorts of statistical analysis against that data. You've got a histogram, you've got 21 days of it per hour, right, for every protocol for Comcast, and now you've got this 1-minute bucket. I'm doing 3 gigs per second. Tell it go calculate the baseline based on some mathematical formula that the user picks. And you come back and say, the baseline says I'm normally doing 1 gig. I'm actually doing 3 gig. It's more than 200%. Perform an action. Right? So
yeah, today we host this in Equinix in DC3 and DC4. So it's building independent, separate transit. We were in Amsterdam, because that's the Usenet central capital of the world. And we are evaluating where the next European location will be. People trust that if you can host in Germany, you can satisfy the most rigid and rigorous privacy requirements. But Amsterdam is also interesting to a lot of our customers. So we'll just have to see. And then probably later this year, something on the West Coast. We've found that the East Coast of the U.S. is fine performance-wise from both Europe and most of the U.S. And we really view we just haven't done the work because the system's fast enough for CDN, except for Europe, except for in Asia, where there may be for HTTPS, you get distance-based performance issues.